In this webcast, we're going to look at molecules that have more than one stereocenter. Generally, these molecules will be chiral. However, there are some important achiral exceptions, like the three examples that you see here. Each of these examples, you'll find a mirror plane in the molecule, and you'll also find two stereocenters. What happens in each of these molecules is that one stereocenter and the other have identical sets of 4 substituents. So a stereocenter has 4 different substituents. You can see that these two atoms, these two carbon atoms in the first example, are stereocenters. But each of them have exactly the same set of 4 substituents. In cases like this, it's possible that the two stereocenters will be mirror images of one another by their location in the molecule. Here you can see there's a mirror plane that bisects the molecule perfectly into half, so that one stereocenter has the opposite configuration stereocenter on the other side of the plane. Because of that, the molecule has a plane of symmetry. Having a plane of symmetry means that it's achiral. Molecules that have more than one stereocenter and are achiral are known as mesomolecules. So the other two examples shown here are very similar. In the case of the Fisher projection, which we can draw with a little more three-dimensionality by adding wedges and dashes, you can see that the top half and the bottom half are related by a mirror plane. You can also see that each of these carbons that I've highlighted have the same set of substituents, but the configurations are exactly opposite. One of them is S and one of them is R. And finally, in the case of this dibromocyclohexane, you can see that there's a stereocenter in the back. It's quite faint. It has a bromine on it, just as the stereocenter that's out in front of this mirror plane. So the mirror plane bisects that cyclohexane into 2 equal parts. The opposite configurations on either side of the mirror plane cancel each other out, effectively making that molecule achiral. For practice, there are some additional examples linked to your notes. This will pull up some structures in 3-dimensional renderings. Go ahead and take a look at those molecules. First thing you should do is identify where the stereocenters are. Then go ahead and rotate the molecule until you can see how the two stereocenters are positioned on opposite sides of a mirror plane. The R and S labels have been helpful in identifying mesomolecules, so now let me show you a trick in ACE that will allow you to rapidly assign R and S to a stereocenter. From the ACE homepage, there's a useful set of tools by clicking at the bottom of the login page where it says Here. That pulls up several tools. We'll use many of them throughout the semester. Right now I just want a Marvin sketchpad, and a Marvin sketchpad can be found in the Stereocenter Configuration Inversion tool. And you're ready to actually learn about that, but I'll let you do that on your own. You can read about it up at the top here. Right now I just want to show you how to assign R and S configurations. Let's look at one of the examples that we've seen already in this webcast. Go ahead and draw the molecule, and now we need to label the stereochemistry in this molecule by using bond types. Right-click brings up the different bond types. These two substituents were both heading down. So now we have the molecule that we've been studying. If we go ahead and use View under Miscellaneous, there is RS Labels, and we can choose All. That brings up the assignment of S and R to those stereocenters. We see that this molecule is meso because those two stereocenters, which have identical substituents, are split into 2 by the mirror plane that runs through the center of that molecule. We can work one more example. The Fisher projection, how does that look in Marvin? We can draw the Fisher projection in the normal way, but at this point Marvin doesn't know that these are stereocenters, so we need to use the bond tool in order to imply, as the Fisher projection does, that this is a wedge type bond with substituent horizontal coming up and out of the plane of the screen. And now immediately Marvin recognizes those stereocenters. We could finish drawing the projection, the Fisher projection, in its 3-dimensional form if we'd like, but Marvin's already been able to assign those. And again, we can see that this is a mesomolecule having 2 opposite configurations on either side of a mirror plane that separates this molecule into 2. The examples in this webcast have shown us that achirality is possible in molecules with multiple stereocenters, as long as those stereocenters have the same kind of substituents and that the stereocenters are on opposite sides of a plane of symmetry in the molecule.